Welcome back to the Marcialis Math Moment. We're going to do special right triangles. This is part 2. We're going to meet and understand the 30, 60, 90 right triangle. And then also talk about how powerful it can be to just memorize these ratios. So first we're going to start with an equilateral right triangle. I know it's not a special right triangle, but it's where we're going to start. So here I have an equilateral triangle with side length 2. So all the sides are 2. And then I draw an altitude from C down to point D. In an equilateral triangle, the altitude is also a median, so it splits the opposite side into equal parts. And so if CB is 2, that means DB is 1. Okay? And that altitude is also an angle bisector. So I already labeled it. It creates a 30 degree angle right here. So now I have a 30, 60, 90 right triangle. And so if I wanted to solve for the altitude, we'll call it A, little a, which is the height of this triangle. We're going to use the Pythagorean theorem. And so I'm going to say A squared, because I don't know what A is. We'll call 1 B, so it's B squared, 1 squared. And it's going to equal C is 2. 2 squared. Let's work that out. We get A squared plus 1 equals 4 squared. Let's solve for A squared. So I get A squared equals 3. Now we solve for A by taking the square root of both sides, and I get A equals the square root of 3. So let me write that over here and leave some space, and you'll see why in a moment. And so we have the side lengths of our triangle. But what if I change the length of this hypotenuse here? Let's say our equilateral triangle was had side lengths of 4. Well, that would mean DB is 2 because it's half of AB. AB equals CB. But what's the height now of this new triangle? Well, let's plug in our values and solve. A squared plus B squared is 2 squared equals C squared is 4 squared. So I get A squared plus 4 equals 16. And I get A squared equals 12 by solving for, I move the 4 to the other side using subtraction. The square root of both sides, I get A equals square root of 12, but I can break that up into 4 times 3. 4 is a perfect square. Square root of 4 is 2, so I pull the 2 out. So I get A equals 2 times the square root of 3. So now, for my new equilateral triangle, the height is 2 times the square root of 3. What if we change it? Again, what do we think the height will be? Let's say I start with an equilateral triangle of side lengths 6. Well, if CB is a median and an altitude and an angle bisector, which it is, DB will be 3. I won't change A. We haven't solved for it yet, so I'll leave it as it stands for now. So let's plug in our values. I have A squared plus B squared is 3 squared equals C squared is 6 squared. That's A squared plus 9 equals 36. Solve for A squared. I get A squared equals 27. Take the square root of both sides. I get A equals, well, 27 is really 9 times 3. 9 is a perfect square. Comes out to be 3. So I get A equals 3 times the square root of 3. And you'll notice a pattern. Whatever the short leg of my right 30, 60, 90 right triangle is, the long leg will be 3 times the square root of 3, and the hypotenuse will just be twice the length of my short leg. So for a 30, 60, 90 right triangle, the ratios will be 1 to square root 3 to 2. Or for the general case, if my short leg is S, my long leg will be S times the square root of 3, and my hypotenuse will be 2 times S. If you can remember this, it's a powerful tool to solve for missing side lengths of special right triangles that are 30, 60, 90 right triangles. So let's try a couple examples. So our first right triangle here is a 30, 60, 90 because I have a 30 labeled in this acute corner right there. And so that means the other acute angle is 60. And so I'm given the short leg, it's 5. I know it's the short leg because it's opposite the 30 degree angle. And so what I like to do, this is in the way. I set up my ratios this way. I have a 30, 60, 90 right triangle, and I have a short leg, a long leg, which is the short leg times the square root of 3, and a hypotenuse, which is 2 times s, or 2 times the short leg. Well, if my short leg is 5, the fastest thing to do is do 5 times 2, that's 10. And then my long leg is going to be 5 times the square root of 3. I just replace s with 5, and the square root of 3 comes down. Done. And let's look at our next triangle. We're given the long leg. I know it's the long leg because it's opposite the 60-degree angle. Don't always trust the scale of your drawings or the drawings that you see. Trust the labels. So I know it's a 30, 60, 90 because I can deduce that this acute angle here is a 30 by using the third angle theorem. So do the same thing. I write my ratios here with s times the square root of 3, and 2 times s. But the issue is I don't have my short leg. I'm given the long leg, which is 6. So a little bit of work to be done, but not too much. If s times the square root of 3 is the long leg, and 6 is the long leg for this triangle that I'm trying to solve, they must equal each other. So then I write 6 equals s times the square root of 3, so I can solve for my short leg. I divide both sides by the square root of 3, cancels that out, and I get s equals 6 divided by the square root of 3, but this is a problem. Again, we have an irrational number in the denominator. We need to rationalize it. We do that by multiplying times 1. So I have 6 over the square root of 3 times 1. Well, that doesn't help me. It needs to be a very specific type of 1. Almost there. Square root of 3 divided by the square root of 3. Anything divided by itself is 1. This helps us because when I multiply across, I get 6 times the square root of 3. The square root of 3 times the square root of 3 is just 3. Now I can simplify. I factor 3 out of the numerator and the denominator, and I'm left with 2 times the square root of 3 over 1, which is just 2 times the square root of 3. So my s is 2 times the square root of 3. My long side, or my short side, which is s, is 2 times the square root of 3. We were given the long side. My hypotenuse is 2 times that, which is 4 times the square root of 3. 2 times the square root of 3 is 4 root 3. And that's it. No Pythagorean theorem involved, no squaring numbers. So, in part 1, we covered our 45, 45, 90. Part 2, we met our 30, 60, 90 right triangle. We used our equilateral triangle to find out how it works and discover those ratios. And those ratios are consistent regardless of what your short leg happens to be or if you're given the hypotenuse. The power of memorizing those ratios enables you to solve some of these problems very quickly. If you're given the short leg of a 30, 60, 90, it's just plugging in that number in front of a radical 3 and then multiplying the short leg times 2. And so you can solve some of these problems very, very quickly. I hope this was helpful. Appreciate you watching. Take care. Stay healthy.